Right, guys. Another important topic that you must understand in your operating systems are the scheduling algorithms. Right? Scheduling algorithms are very important. You need to understand scheduling algorithms because this is how the queue is managed within the operating system. Right? So to schedule is just to actually queue and manage the applications that are supposed to run in the main memory. So there are several scheduling algorithms that you have to understand, but maybe I will teach you the most important ones that you need to know at this stage. So what I'm going to do is I'm going to talk about the basic concept of scheduling algorithms, scheduling criteria, and then maybe scheduling of threads versus scheduling of processes. That's what I'm going to talk about, right? So look at what we are saying. We are saying a maximum CPU utilization is obtained with multi-programming. What are we trying to say? We are saying if we allow many processes to compete for the processor at any point in time, it actually means we can maximize the amount of work that the processor should be doing at each and every point in time, right? So a process that is executing consists of a cycle or CPU execution where we are saying the process can run. When it runs, it reaches a point where it needs input or some output in a way. So that moment the process blocks or waits. The CPU is no longer in use, right? So in other words, we are saying the CPU operates in bursts followed by a CPU bursts followed by input output bursts, right? So during the CPU burst, it means the process is running, right? Input output burst, it actually means the process is now waiting for some input or is waiting for some output to occur before it starts running again, right? So it means usually most processes do not need the processor all their time. Rather, they would need the processor during the CPU burst. During the input output burst, they may not need the CPU. So what does that mean? It means during that time, the CPU can be used by other processes, right? So look at an example there, the CPU burst, which is this one, the CPU burst, right? So look in the input output burst, it's waiting for input output. Then look, this is now a CPU burst. This is an input output burst. This is a CPU burst. So do you see that a running process doesn't need the processor all the time? Because it runs, waits, runs, waits, runs, waits. So this is the reason why if we want to maximize CPU utilization, we need more than one process to be running we need more than one processes to be running at each and every point in time. When one process is waiting, the other process is utilizing the CPU. When that process utilizing the CPU waits, another process gets in, and so on and so forth. So that is how we can maximize throughput of a computer. So a CPU scheduler selects among the processes in the ready queue and allocates a CPU core to one of them, right? So a queue may be ordered in various ways. CPU scheduling decisions may take place when process switches from running to waiting state. When a process switches from running to ready state, when a process switching from waiting to ready state, when a process terminates, and so on and so forth. For all these situations, there is no choice in terms of scheduling. A new process, if one exists in the ready queue, must be selected for execution. For situations 2 and 3, however, there is a choice, right? So what are we saying? We are saying if we have a single process that is running at any point in time and we don't have another process, it means the CPU will not be utilized fully, because during the times a process is in a wait situation, it means the CPU is not being used. The CPU will lie idle some of the times. Right, so scheduling simply means ordering the processes that wait to get the CPU. So when scheduling takes place, only under circumstances 1 and 4, the scheduling scheme is non-preemptive, right? When we are saying non-preemptive, we are saying this is a scheduling algorithm which, if the processor gets the CPU, it runs until it gets to the end. It doesn't relinquish the CPU during the time of running. Otherwise, some other processes are preemptive. It means a process that is preemptive, the moment it waits for a resource for input or output, it relinquishes the CPU. That's a preemptive process. A non-preemptive process is a process which, once it gets hold of the CPU, it doesn't relinquish the CPU even if it's waiting. Right? So under non-preemptive scheduling, once the CPU has been allocated a process, the process keeps the CPU until it releases it, either by terminating or by switching to the waiting state. Virtually all modern operating systems, including Windows, Mac OS, Linux, use preemptive scheduling algorithms. So preemptive scheduling can result in race conditions when data are shared among several processes. Consider the case of two processes that share data, right? While one process is updating the data, it is preempted so that the second process can run. The second process then tries to read the data, which are in an inconsistent state. The issue can be explored in another chapter, of course. We are not going to talk about it here, but that's the truth to say. Whenever two processes are sharing the same data section and both the processes are preemptive, it actually means the possibility of race conditions come in. A situation where one process wants to access data, but the other process is not completed updating it. Maybe it has gone to a wait condition before updating the data. That needs to be used by another process. That is what we mean by race conditions. A dispatcher module gives control of the CPU to the process selected by the CPU scheduler. It involves switching the context, right? Then switching to user mode, jumping to the proper location in the user program to restart that program, right? So you still remember the concept of context switch we talked about in the previous lesson. So this is exactly what we are talking about here, to say a dispatcher is responsible for context switch or for changing the programs, switching, interleaving the programs within the CPU. So look at an example there where we're saying process 0 is executing here. Then process 0 is now being saved. This is switching, it means the process of switching the context has started here, right? Now we restore the context or the process control block of process B. Here we have been saving the process control block of process A. Here we are restoring the process control block of process B, and then process B is now running. So this is the process of changing from one application or thread to another. We simply save the state of the current process control block and then we allow it to exit. Then we take the process control block of another program which was waiting or in the queue, then we place it into the processor, and we go to the point where it last terminated, where it last waited, then we continue running it. So during that process, there is what is called a dispatch latency, the time it takes for a dispatcher to stop one process and start another one. That small moment is called dispatch latency. So scheduling criteria, what do we consider when we are scheduling processes in the queue? We think of CPU utilization. We want to keep the CPU as busy as possible to increase throughput, the amount of work that the CPU will do. So throughput, the number of processes that complete their execution per unit of time. Say how many processes have completed their tasks within maybe a minute or an hour or so. Then the turnaround time is the time to execute a particular process. From the beginning of executing a process to its end, we call that the turnaround time. Then the waiting time, that is the amount of time the process has to wait in the ready queue before it has been dispatched into the processor. Then we want to think about response time, the amount of time it takes from when a request is submitted until the response is produced. So these are the things that we consider to say, is processes being executed efficiently or not. These are some of the things that we look at: CPU utilization, throughput, turnaround time, waiting time, and response time. So look at an example there. Our first scheduling algorithm, first come, first served scheduling, right? Look at what is happening. We have processes 1, 2, 3. The best time, it means the time it takes to execute a process. Process 1 needs 24 seconds, process 2 needs 3 seconds, process 3 needs 3 seconds. So suppose the processes arrive like that, to say P1 comes first, P2 comes first, then P3 comes last, right? So look at the Gantt chart, the way the processes will be executed. It means process 1 will take its 24 seconds, then it terminates. Then process 2 starts at 24 seconds, going to 27, it terminates. Then the process 3 starts at second 27 to 30 to second 30. So look at what is happening there. We've said process 1 starts at T0, process 2 starts at T24, process 3 starts at T27. So if we want to find the average waiting time, look at what is happening there. It means process 2 is going to wait 24 minutes for it to start executing. Then process 3 is going to wait for 27 minutes for it to start executing. So if we want to find the average waiting time, look, we add 0 plus 24 plus 27 divided by 3. So the average waiting time for each process is 17 seconds there. So suppose the processes arrive in this order. Look, if they arrive in the order where we start with process 2, then we got process 3, we got process 1. Look at their waiting times. It means process 2 will wait for 0 times. Process 2 will wait for 0 milliseconds. Then process 3 will wait for 3 seconds. Then process 1 will wait for 6 seconds. So look at what is happening. The waiting time for process 1 is 6 seconds. The waiting time for process 2 is 0. The waiting time for process 3 is 3. So the average waiting time, look at what is now happening. The average waiting time is now 3. Do you see that if we change the order in which these processes arrive, if the shorter processes, if those processes which take a shorter time to execute, if the shorter processes come earlier, it means the waiting times for all the process, the average waiting time becomes shorter. The computer becomes more efficient when we consider the average waiting time for executing all the processes. So it means the first come first serve scheduling algorithm has a problem that if the longer processes arrive earlier, the average waiting time for all the processes will be longer, which means our computer is becoming an inefficient one. So this is what we call the convoy effect. Short processes behind long processes will wait for long, yet they are very short processes. So it actually means we may need an algorithm which checks the best times of processes so that the short processes execute first, and therefore we limit the total amount of waiting times for all the processes, or the average waiting time. Right? Now let us consider CPU bound and input output bound processes. If we are saying a CPU bound process, we are simply saying that process takes most of its time utilizing the CPU. If we are saying an input output bound process, it means that process takes more time waiting. Right? There are processes which utilize CPU more. They are called CPU bound processes. There are processes which spend most of their times waiting for resources than utilizing the CPU. We call those our input output bound processes. So now look, we are now looking at another algorithm which is called a shortest job first, which can now utilize the disadvantage of the first come first serve. Right? This one associates its process with the length of the CPU burst. It uses this length to schedule the process with the shortest time. Shortest job first is optimal. It gives minimum average waiting time for a set of processes. Preemptive version for shortest job first is called shortest remaining time first. Right? So how do we determine the length of the next CPU burst? We ask the user, or we estimate. Right? So the shortest job first, look at what happens. We've got our processes P1 there. We now have an example. P1, P2, P3, P4. Look, P1 has 6 seconds, P2 has 8, P3 has 7, P4 has 3. So look at what is happening. We are going to start by executing P4. Then we come to P1. Then we come to P3. Then we come to P2. P2 is going to be the last process to be executed there because it's taking the longest time. So look at the average waiting time there, which is 7. Right? So of course, the process of determining the next CPU burst, we don't want to worry much about it, but look at what is happening. What we only want you to understand is that if we have processes assuming that they have arrived at the same time, we are simply choosing the processes with the shortest time. We execute those first in order to make sure that all the process will equally enjoy a shortest waiting time within a queue. Right? So now let us talk about the shortest remaining time first algorithm, which is now a better version of the shortest job first. The shortest remaining time assumes that even the job that is running, we can preempt it if a shorter job arrives. So this is now a preemptive version of shortest job first. Whenever a new process arrives in the ready queue, the decision on which process to execute next is redone using the shortest job next algorithm. In the shortest job next algorithm, the minimum average waiting time is achieved even better compared to the shortest job first, because we are saying if a process is executing and a new process arrives, we start comparing again. We are comparing the length of all the processes, including the process that is currently running. If the process that is holding the processor right now still has the remaining time which is longer than the process that has arrived, it means the running process is going to be preempted. So look at the example there. We have got P1 which arrives at T0, P2 which arrives at T1, P3 which arrives at T2, P4 which arrives at T3. Look at the best times. Each process, P1 has the best time of 8, P2 4, P3 9, P5, P4 5. So look, when P1 executes from it, P1 executes from first to the second, from 0 to 1 a second. Why? Because P2 has not arrived. So when P2 arrives after 1 second, it means P1 still has 7 seconds to execute, but P2 has 4 seconds to execute. So it means P1 is going to be preempted. Then P2 gets the CPU. It executes for 1 second. When it executes for 1 second, P3 arrives. When P3 arrives, the comparison is done again, and then it shows that P2 is going to continue running because it's left with 3 seconds. Right? When P4 arrives, look at what is happening. When P4 arrives, it is arriving at 3 seconds. When P2 is already left with 1 second. So it means P2 continues executing. So P2 is going to execute up to finish without having been preempted. Then P1 has been preempted after 1 second. Then now after P2 has finished, it means we are now comparing P1 with now 7 seconds, then P3 with 9, P4 with 5. So it actually means a P4 begins executing because it is the one with shortest remaining time, and it is going to execute until it completes. When it completes, a P1 which now has 7 seconds comes back because it's now shorter than P3. Then it executes to completion, after which P3 is then allowed there. So look at the way we are going to calculate the average waiting time there. Then we have another algorithm called the round robin algorithm. Each process gets a small time called a quantum, right? We have got a rule in round robin to say each process is going to execute for 2 milliseconds. That's a rule. No matter how long the process is, if it executes for 2 seconds, it should be allowed to exit. If it executes for 2 seconds, it should be allowed to exit, so that processes take turns to acquire the processor. So that time we allocate each process is called a time quantum, and it's usually 10 to 100 milliseconds. After this time has elapsed, the process is preempted and added into the end of the ready queue. If any processes are in the ready queue and the time quantum is Q, each process gets 1 over n of the CPU in time chunks of most Q time units at once. No process waits more than n-1 of Q time units. The timer interrupts every quantum to schedule the next process. So its performance, where the queue is Q large, in first come first serve, the time quantum is small, then it actually means that more dispatches of processes will take place if the time quantum is small. If the quantum is large, it actually means a preempting processes becomes less. So Q must be large with respect to the context switch, otherwise an overhead of context switching becomes too high. So what does that mean? It means the smaller the time quantum, the more we need to change the programs, and then the greater the overhead that the context switch takes. So there is an example of round robin. We are given the process 1, process 2, process 3, and they have 24, 3, 3, and our time quantum is 4, which means a process 1 is preempted at 4, then process 2 gets in, which has 3 seconds, it's executed to the end. Process 3 gets in, it has 3 seconds, it's executed to the end. Then process 1 comes back, and it's going to take all the remaining time quantums. Why? Because there is no other process that is now existing within the queue. So this is what we mean by round robin. So look at what happens. Like I was explaining, to say the greater the time quantum, the less the context switches that are going to take place. The smaller the time quantum, the greater the number of context switches that are going to take place, and hence the overhead of switching the context. So when this algorithm is being designed, there's need to think forward to say what exact time quantum do we need to place so that the computer increases its throughput. That is the idea behind scheduling. We always want a computer to increase its throughput. So basically, this is round robin. So the issue of turnaround time, as it varies with time quantum, you need to also look into it. I'm not going to explain it here, otherwise my lecture is going to be too long. Then we talk of priority scheduling, where each process is given a priority number to decide which process to execute at each and every point in time. So a priority is an integer number associated with each process. The CPU is allocated the process with the highest priority or at any point in time. So priority scheduling can also be preemptive or non-preemptive. When it is preemptive, like we said, it means that a process, if a process that is currently running is of a lesser priority than the process that has arrived in the queue, it means the process in the queue can actually lead to preemption of the process that is currently running. If it's non-preemptive, it means a process that has been allocated a processor is going to run up to completion before relinquishing the process. So an example of a priority scheduling is shortest job first, because it prioritizes processes with short burst times, right? However, the problem with priority scheduling is starvation, which means some other processes will take very long to actually run. Because we have the problem of starvation, we can also do the process of aging to actually consider those processes that take too long in the queue. It means the longer the process takes in the queue, the higher the priority of that process is going to be incremented, and therefore it can soon execute. That's the idea of trying to counter against starvation. So look at an example of priority scheduling there, where we have best times, then we have the priorities. It means the process with the highest value there, with the highest priority, is P2, which then starts to execute, then followed by P5, followed by P3, followed by P3, yes, but the fact that P3 is going to arrive later, so look at what is going to happen there. Then if you calculate the average waiting time, then it becomes 8.2. So this is an example of priority scheduling. Look, this is now another example of priority scheduling mixed with round robin. Processes have got priorities. At the same time, there is a time quantum that makes round robin necessary, right? So like we talked about, to say we have been assuming that each processor has a single queue. When we're talking about these algorithms, we were assuming that each processor has a single queue at hand. But in the real world, each processor can have many queues. That's when we talk about multi-level queues. You still remember when we were talking about scheduling in the previous lesson, we were saying a processor cannot only have a single queue, but there can be many queues, queue, the ready queue, those for the queue for those waiting for input output, the queues for those that have been faced interrupts, and so on and so forth. So the management of the queue is not as simple as we are doing here. Here we are simply simplifying concepts so that you understand them. But the real world doesn't make simple queues like we've been doing. So look at an example of a multi-level queue. Maybe you need to take time to understand this. Go into the slides, look at it, make some more research to understand what we mean by multi-level queue and how complex the queues can be managed in the real world operating system. Of course, we've been simplifying algorithms here, but in the actual computer, we have very complex processes to take and very complex algorithms to manage applications that are waiting to run, right? So, ladies and gentlemen, let me stop here. We need to know more about the queues. Then the difference now between scheduling the queues and scheduling the threads. This is now thread scheduling as being opposed to processes, right? Remember, a process is a complete application. A thread is a sub-process within a process. So a thread is a lightweight process. A process is a complete application. A thread is a lightweight process. These are some of the things that you actually want to understand. So this is now pre-thread scheduling, whatever the techniques of various operating systems from Windows to Unix to Linux. I'm not going to get into that. I wanted you to get the basics of scheduling and the various algorithms in a simplified way that will enable you write your examination and understand operating systems at your level of study and having a general appreciation of how computers work. So thank you, ladies and gentlemen. I will come again with another lecture when I have time.